For the longest time, a stable wormhole was pretty much considered impossible. But a new paper is challenging all of that. So today, we're going to break down this new theoretical model that might just be the first tiny step toward making cosmic shortcuts a reality. Let's dive in.
Okay, let's be real. The idea of hopping through a wormhole? It's total science fiction, right? For now, anyway. So what's the big holdup? What's stopping us from making it a reality? Well, it really all boils down to one single, massive problem that has stumped physicists for generations.
We all know the dream, right? A tunnel through space-time, the ultimate cosmic shortcut. But here's the thing. For literally anything to exist in our universe, a star, a planet, even a pencil on your desk, it has to be stable. And that, right there, is where the whole wormhole dream has always hit a brick wall.
Yeah, this is it. This is the absolute core of the problem: stability. See, for something to exist, it can't just shatter at the slightest touch. It has to be able to handle little bumps and disturbances. And this one simple rule of the universe has been the biggest hurdle for anyone even thinking about building a wormhole, even on paper.
So let's talk about this instability problem. What exactly is it? And, this isn't some minor technical glitch. We're talking about a fundamental, show-stopping flaw that has pretty much destroyed every wormhole model ever proposed.
So what do physicists really mean when they say unstable? Okay, picture this. You've built this incredible, super detailed sandcastle right at the edge of the water. But the moment a tiny breeze blows or a single drop of water hits it, poof, the whole thing just collapses. That's exactly what we mean by instability. And for a wormhole, this is even more dramatic. It means the very act of trying to send something through it, even a single photon of light, would cause the entire tunnel to instantly collapse into a black hole. Not exactly a great travel plan.
This is a fantastic way to picture it. On the one hand, you've got a stable system. Think of it like a marble at the bottom of a bowl. You can nudge it, push it around, but it's always going to roll right back to the center. It's stable. But an unstable system, that's like trying to balance a pencil perfectly on its pointy tip. The tiniest vibration, a whisper of air, and it's over, it falls. Every wormhole model before this one was like that pencil.
And believe me, scientists have tried everything to solve this. The simplest, most elegant models? Nope, turned out they were totally unstable. Okay, what if we tried to prop it open with powerful electric or magnetic fields? That didn't work either. Seriously, for decades, it just looked like a stable wormhole was fundamentally impossible within the laws of physics as we know them, a complete dead end. But this new paper is suggesting there might finally be a way forward.
So how in the world do you solve a problem that's been a roadblock for generations of physicists? Well, you need a totally new approach, a new blueprint. And that's exactly what we see in this paper from K.A. Bronnikov and his team. And you should really think of it less as a single discovery and more like a very, very specific and kind of weird recipe.
You see, the real genius here isn't one single magic bullet idea. It's all about how they combined three very specific theoretical ingredients. Now, these ingredients weren't totally new. Physicists had kicked them around before, but no one had ever put them together in this exact way. And by doing that, they created something that, at least on paper, is brand new, a potentially stable wormhole.
So what are these three key ingredients? Okay, ingredient number one, the geometry. They start with a very specific mathematical structure called an Ellis wormhole. You can think of this as the basic shape, or the mold, for our wormhole. Second, the field. They thread this shape with a really bizarre type of magnetic field, one that has no source. The great physicist John Wheeler called this charge without charge. It's some seriously weird stuff. And then, ingredient number three, and this is the really critical one, the fluid. They fill it with something called a phantom fluid. Now this stuff has negative energy density, which means it basically pushes outward instead of pulling inward. It acts like a kind of anti-gravity scaffolding, propping the wormhole open and fighting against that urge to collapse.
All right, so you've got the recipe, you've mixed the ingredients, you've baked your theoretical cake. But now comes the most crucial part of all, the stress test. Will it actually hold up under pressure? Because a model on paper is one thing, but you have to prove it can actually survive being poked and prodded.
So how do physicists do this? They perturb the model. That's the fancy word for it. Basically, they hit it with tiny mathematical shockwaves in a simulation. They jiggle the equations around to see what happens. The big question is, does it wobble for a second and then settle back down like our marble in the bowl, or does it just completely fall apart, like that pencil on its tip?
Okay, first up is test number one, spherical perturbations. This is the most basic kind of test. It's like checking to see if the wormhole's throat would just collapse in on itself if you squeezed it evenly from all sides. And this is the most common and, frankly, the most dangerous type of instability you have to worry about.
And the result? It's stable. It passed. Against this fundamental test, the model actually holds together. I mean, this was a massive first step.
But okay, one test isn't enough. You gotta be thorough. So they moved on to a much trickier test, axial perturbations. Now this is way more complex. This is like sending twisting, uneven shock waves through the wormhole. It's a much more realistic test for the kind of chaos you'd find in the real universe.
And the result of this much tougher test? It was stable. Again, the model survived even these complex, twisting disturbances. This had literally never been done before. This was a genuine first in the history of theoretical physics.
So what does this all mean? What's the big takeaway? It's super easy to get carried away here, so let's be really clear about what this is and what it isn't.
So, does this mean we're about to build a wormhole drive for our spaceships? No, not even close. Remember that recipe? All of those ingredients, the phantom fluid, the source-free field, they're completely theoretical. We have no idea if they even exist or how we'd make them. What this is a mathematical proof of concept. It's a demonstration on paper that a stable wormhole could exist without breaking the laws of general relativity. And that's huge. It's a tiny glimmer of possibility where before there was just nothing.
And really, the authors of the paper say it best themselves. They call it, and I'm quoting here, the first example of a stable wormhole model in general relativity. That is the landmark statement. It carves out a whole new path for physicists to explore.
And that really is the thought I want to leave you with. For almost 100 years, stable wormholes were basically written off as impossible, forbidden by the laws of physics. This paper comes along and suggests, hey, maybe they're not impossible after all. And that makes you wonder, right? If that long-held assumption was wrong, what other impossible ideas out there are just waiting for someone to find the right recipe?